Hi, this is Algebra I, Lesson 8-2, Quadratic Functions in Vertex form. In this lesson, we'll be able to graph quadratic functions using the vertex form. The key vocabulary is vertex form of a quadratic function. Let's start with critique and explain. Ali states that the two graphs shown may look different, but they are actually the same figure. Esteban disagrees, stating that they are different figures because they look different. So, part A, give one mathematical argument to support Esteban's thinking. So he says they look different, so they're different. Is it true? How can we back up his reasoning? So we're looking at what's different, what makes it different. So they look different, but they also look similar. But what are the things that you notice that are different? Probably the vertex, right? So when x is equal to 0, the y's are different. When x is equal to 1, the y values are also different. If you look at this line, that's where the graph A starts, facing upward. And this line is where graph B has its vertex, right? And if you look at the width may also look different. Okay, so those are the things you can notice and point out. Let's write that. There we go. The vertex of graph A is 0, 4. If you look at the grid line, this is 10, so each grid represents 2. 2, 4, 6, 8, and 10, right? So the vertex of graph A starts at 0, 4. The vertex of graph B is 0, 0. Okay, that's different. So the graphs are different. Part B, give one mathematical argument to support Ali's thinking. Ali says the graphs shown may look different, but they're actually the same. So what if we move graph B 4 units above, 4 units up, right? Then would they still be the same? Would they be the same? Would they still be different? So the vertex may actually be the same, right? The vertexes, vertex would be the same. Would the other points be the same? So let's look at some points, okay? The points at x equals -1. So graph B has -1, 4. And then graph A looks like it has it on 8, -1, 8. So if you move graph B 4 units above, then you're moving the y value, the value of y, right? So 4 plus 4 units above, it's going to move up. So for x is equal to -1, yeah, that point moves up 4 units, then it's on the same point as graph A. What about the other point? When x is equal to 1, we have this point where it's 1, 8 as well. And then for graph B, we have 1, 4. So if we move the point 4 units up, then we'll have exactly 1, 8. So these points work. The vertex will move exactly on the vertex of graph A as well. If you pick other points, they should also be the same. So if we just move the entire graph 4 units up, then graph B lies on graph A. So yeah, we could say that they are the same. Let's write that down. Okay, the points at x equals -1, 0, and 1 in graph A are each 2 units above the corresponding point in graph B. So the graphs appear to have the same shape. Part C. Who do you agree with? What argument can you give to justify your reasoning? So who speaks out to you more? Who do you agree with more? Is it Esteban or Ali? There isn't a correct answer as long as you can reason it mathematically and logically. So if you say Ali, you can say, oh, because the point at each value of x in graph A is 2 units above or 4 units above the corresponding point in graph B. But it's not 2 units here. It's actually 4 units. They're the same, right? So if you translate graph A above 4 units or graph B down to 4 units, they would be the same. If you choose Esteban, you would probably say they're still different because yeah, the shapes could be the same, but they start at a different point. So all the points are different, so technically they're still different, okay? It could be either way. There are similarities and differences between those. So choose one. I'm gonna choose Ali. You can choose Esteban. Just make sure you explain and reason it out. So there you go. Ali, because the point at each value of x in graph A is 4 units above the corresponding point in graph B. And if you translate graph B down 4 units, they would also be the same. So that's just an example of comparison and for you to get started thinking about different quadratic functions. We're going to look at quadratic functions in vertex form today. So the lesson essential question is, how can the vertex form of a quadratic function help you sketch the graph of the function? Which you can tell that the vertex form of a quadratic function will be very helpful for you to graph the function. Let's look at example 1. Understand the graph of g of x equals x squared plus k. So we did look at the coefficient a and how that changes the graph in the previous lesson. Today, we're going to see how k, which is added on the quadratic term, will change the graph. So, how does the graph of g of x equals x squared minus 4 compare to that of the parent function, x squared? We're going to graph the function g and the parent function f. So parent function f is the blue one, okay? That is the parent function x squared. Without any transformation, that's just where you start with the graph x squared. And then if you figure out the table of g of x, okay, when x is 0, 0 minus 4 is negative 4. When x is 1, 1 squared is 1, minus 4 is negative 3. When x is 2, 2 squared is 4, minus 4 is 0. And when x is 3, 3 squared is 9, minus 4 is 5. And so on. So look at the points. 0, negative 4, 1, negative 3, 2, 0, 3, 5, and then if you have x is negative 1, Negative 1 squared is still positive 1, so it should still be negative 3. And then negative 2 will be 0, negative 3 would be 5. So then you plot the points and then draw the curve. And that's the curve of G. And then you compare these graphs. How did it change? It's not changing the wideness, right? It's not changing the width. There's no slope, there's no A, right? The coefficient. So it's not getting larger, broader, or like narrower. It's still the same shape, but it's gonna move down. All your points are moving down, okay? How many units? Exactly K units. Minus 4 means K is negative 4. So that means all your points is gonna move down 4 units. So that is what kind of transformation is it? K is responsible for a translation, okay? And A, the coefficient, is going to be responsible for both reflection and stretches, okay? Or compression. So K is just translation up and down, up and down. Okay, let's look at chart number 1. How does the graph of each function compare to the graph of the parent function x squared? So when you compare them, you have to compare it to the parent function. Compared to the parent function x squared, it translates the graph vertically k units. So those are the vocab, the phrases that you need in order to explain the comparison, okay, the changes. So the vertex of the graph is at 0, k. So in this case, you're going to say x squared minus 4 translates the graph of the parent function vertically 4 units down. And the vertex of the graph is at 0, negative 4. The value of k does not affect the axis of symmetry. It just translates the graph down 4 units. Okay? So let's look at try number 1A and B. See if you can explain it by yourself using these phrases. Does it translate? How does it translate the parent function? Vertically, horizontally. Horizontally is left and right. And k is a vertical translation. It moves the graph up and down. We'll look at horizontal translation later, okay? But right now, you want to look at example 1 and describe this. So pause the video and come back when you are ready for answers. Okay. Are you ready? So, the parent function x squared, compared to the parent function x squared, how does the graph change for h of x? So, your parent function is the first term, right? Whatever your first term is, that should be your original values for your range, right? And then you just add 3 for all the values of y, right? Whatever is x, whatever answer you get for a specific x, you just add 3 for each value, right? So all your points are going to move 3 units up. So that's your translation. So we can say h of x is a translation of 3 units up from the parent function. The vertex moves up 3 units, and the axis of symmetry is the same. What about part B? J of x is a translation of how many units? 2 units. Is it up or down? It's negative, so it's going down from the parent function. The vertex moves down 2 units, the axis of symmetry is the same. Okay? There we go. Okay? We've already gone through the transformations, so this shouldn't be too hard, but it should be a good review of what we learned in the transformation topic. And we're just focusing on the quadratics. Let's look at example 2. Understand the graph of g of x equals parentheses x minus h squared. How does the graph of g of x equals parentheses, very important, x minus 3 squared compare to that of the parent function x squared? So notice, compared to the parent function, what's the difference? Are we adding k? It's a little bit different with adding k from the entire thing. Why? Because you need to remember the order of operation. If you have x squared plus k, what do you solve first? The x squared, and then you add k, right? What if you have parentheses x minus h and then square? And then you have a k here. What do you solve first? You solve the parentheses first, and then you solve the square, and then you add k. So h and k are not the same. Even though it's addition and subtraction, they're not the same. That's why they're represented differently with different letters. Okay? So h is subtracted first, and then we square. That is going to change the answer completely. So in this case, you'll see that the graph is moving horizontally instead. And note that it's minus h. So if you subtract h from x first and then square it, your y values are still going to be the same as the parent function, but your x moves to the right. Okay, so look at this one. G of x is x minus 3, parentheses, and then squared, right? So your h here is not negative 3. Your h is positive 3. So what does that mean? If h is positive 3, it's moving horizontally. Okay, h stands for horizontal movement. So horizontally, it's moving 3 units to the right. So if it's positive, it's to the right. If it's negative, it's to the left. But you must keep in mind that x minus h is the form. So if you see x minus 3, that means h is positive 3. So your graph is moving 3 units to the right. Okay? So I think that's pretty self-explanatory after the vertical translation. But just make sure you read this common error. You may think that the graph of this would be a horizontal translation of the graph of parent function to the left because there is a negative sign, but it's actually a positive translation because h is positive. Okay? Because your range is talking about your y, right? So g of x is what your expression is representing of. So we're plugging in x, that's your input, and then we're getting output. So that's why when we're thinking of x, it's flipped backwards, okay? For range, if we just change the values from the entire thing, that changes the range, and so that moves your numbers up and down, so that's pretty easy to remember. But for x, for domain, it's backwards, okay? Because your equation itself, your function itself is written in terms of y, or your function. Okay? It's not x equals something y plus something, right? So that's why they're backwards. All right, let's look at try number 2 and see if you can figure out the horizontal transformation here, horizontal translation here. Write it in phrases. Pause the video and come back for answers when you're ready. Okay, are you ready? So, compared to the parent function x squared, how does h of x move? You have x plus 1, the whole thing first, and then squared. So remember, your form is x minus h. So in this case, if it's x plus 1, what is it really? X plus 1 is really x minus negative 1. Right? So then your h is negative 1 here, right? So how does the graph move? The graph moves 1 unit to the left, okay? This is a horizontal translation. And the vertex and the axis of symmetry are shifted 1 unit left as well. Okay, what about j of x? You see x minus 5 inside the parentheses. So if you look at the form of horizontal translation, x minus h squared, your h is positive 5, right? So you are translating 5 units to the right. So the vertex and the axis of symmetry are also shifted 5 units right. Okay? Let's look at example 3, conceptual understanding. Understand the graph of f of x equals a, parentheses, x minus h squared plus k. And now we have a, h, and k as constants. They're going to be numbers in different forms, okay? Your parent function, remember, is x squared. And we're adding these numbers, and these all represent different transformations, okay? So that's going to be the form of transformation for the quadratic functions. What information do the values of h and k provide about the graph of f of x equals x minus h squared plus k? We're going to graph several functions of this form. So first of all, let's look at this one. So a is going to be 1, okay? There's no a here, which is times 1. So this is when a is equal to 1. But here, h is 1 and k is equal to negative 3, okay? So if you look at the graph, you'll notice that the vertex is going to be h comma k, right? 1 comma negative 3 is your vertex, right? And that's exactly how you moved your graph, because your vertex starts from 0, 0, right? 0, 0 in your parent function. And then you're just translating all the points on the graph, k units up or down, and h units left or right. So your vertex, starting from 0, is going to move up or right, k units, and then left or right, up or down k units, left or right h units, right? So then your vertex is simply just going to be h comma k, okay? So from the original parent function 0, 0, this is parent function f of x, x squared. Your transformation g of x is going to be 0 plus k, and then comma 0 plus, 0 plus h, because that's x, and that's k. 0 plus h and 0 plus k, which is just h comma k, okay? So look at this graph, x minus 1 squared plus 2 has a vertex of 1 comma 2. How do you graph this? You need to plug in different values for x and solve for y. You need to draw a table and then graph point by point and then draw the curve. There's no easier way. Okay? You shouldn't use graphing calculators to graph it for you. You should also know how to graph parabolas. Okay? If you need more practice, let us know. And the third one as well, you'll see that the vertex is h comma k. So -2, so that's when h is -2 because that's +2, right? And then k is -1. So -2 comma -1 is right here. So the values of h and k determine the location of the vertex when you see the quadratic equations in this form. And the axis of symmetry is always x equals k, because that's going to be x equals something. So x is always going, x equals h. X is always going to be moving h units. So x has to be h. In this case, h is 1, so x is 1 here. X is -2. And this one, this line of symmetry is x is equal to 1. You see that? Yeah, that was example 3. So, on the next page, how does the value of a affect the graph of f of x equals a x minus h squared plus k? And now, we also want to look at a. How does a change the graph? As we have looked at it in the last lesson, your a will change the shape, like the wideness, the width of your graph. Okay, it may make your graph go wider or narrower, depending on the magnitude of your a. So if you have an absolute value of an a, you'll easily be able to see, oh, is it going to get wider? Is it going to get smaller? So if you remember from last lesson, if a is less than 1 but greater than 0, okay? It has to be greater than 0 because it's absolute value, but I still want to give you that limit because negative is something else. It's not the width, it's the reflection, okay? Then the graph gets, so that's decimals, the graph gets wider, okay? That's going to be point something, or 1/2 in fractions, or 1/5, or 2/7, whatever that's less than 1 will get you a wider graph. Gets wider, okay? When a, absolute value a is greater than 1, the graph gets narrower, okay? So keep that in mind. This is, you need to be able to break the form down and separate the transformation, the different transformations. A will change your shape. Okay, h and k just translates your whole graph. Okay, so let's look at this vocabulary. The vertex form of a quadratic function is exactly that. F of x is equal to a, parentheses, x minus h, parentheses close, square plus k. Okay, so here a, h, and k are not variables. They need to be numbers. Whether they're 1 and they're not there, they're not visible, they're still there. They're still going to be there. Okay, h and k, in order for them to be not visible, they need to be 0, not 1, right? Because it's addition and subtraction. If you add 0, if you subtract 0, it doesn't change the graph, right? So those are numbers in different forms. That's just the vertex form. This is not a specific form of an equation. Okay, it's just a vertex form to identify which parts of the equation is what. Okay, let's look at try number 3. How does the graph of f of x equals -3, parentheses x minus 5 square plus 7 compared to the graph of the parent function? So please tear this apart and identify the parts and write as much transformation you see compared to the parent function. Okay? Come back when you're ready for answers. Okay, are you ready? So what are the parts? We have A is equal to -3, and then so absolute value of A is +3, right? And then H is x minus 5, so H is just +5. Remember that. K is +7, okay? So using this information, you're going to describe. What does A do? It makes it narrower or wider or narrower, right? What does the sign do? The negative sign is a reflection, okay, over the x-axis. And then H and K gives you the vertex, and also they give you the translation, okay? So H means horizontal translation, K stands for vertical translation. So you're gonna move 5 units right, and then 7 units up. And then that means reflection. We have a reflection because A is negative. And also magnitude of A is greater than 1. So it's going to make the graph narrower. So let's summarize that and write that down. Put it together. Okay, so the graph of F is translated up 7 units and right 5 units. It is narrower than the parent function and opens upward. There you go. Where's the reflection? Oh, opens downward. That's the reflection. So if you just want to write, oh, it's reflected across x-axis, and the graph gets narrower, and the vertex, let's add the vertex. There we go. So the vertex, which is 5, 7, moves up 7 units and right 5 units as well. Okay, now we have identified everything. Let's look at example 4. Graph using vertex form. So now, let's practice graphing. How can you use the vertex form of a quadratic function to sketch the graph of the function? Yes, you still have to plot the points. But if it is in vertex form, it makes your life easier because you can easily locate what? The vertex, because your H and K is right there. So then you start with the vertex, right? So look at this form. F of x is equal to -2, parentheses x plus 1 squared plus 5. You can easily see that H is 1, or -1, sorry. K is 5. That means your vertex is -1, 5. Easy. So you start with -1, 5, and you know that the axis of symmetry is going to go through your vertex, which is x equals -1. And so you're going to create a table. You're still going to create a table. There's no easy way. But you know where to start. So -1 is going to be the point of change, right? So -1, 5 is 1 point. So then you're going to start plugging in points for values less than 1 and greater than 1. 0 and 1. Okay? So then you'll figure out, you'll plug it in. -2 plus 1 is -1, square is 1. So times that is -2 plus 5 is 3. And then 0, same thing. 0 plus 1 is 1, square is 1, so times that and plus is 3. And then 1 plus 1 is 2, 2 squared is 4, 4 times -2 is -8, plus 5 is -3, and same for -3 for x as well. So then you plot the points and then you draw a curve through them. Okay? That's how you graph it. So let's try number 4A and B. Start with the vertex and make a table of values and graph the parabolas. These are already in vertex form, so it shouldn't be too hard. Pause the video, see if you can graph it. Graphing papers are provided in a resource station in our classroom. If you have a graphing paper, that's great. Please graph it and come back when you're ready. Okay, so let's look at 4A. G of x is -3 times x minus 2 squared plus 1. Your A is -3, but that's not really important in graphing. Your H is 2, K is 1, so your HK is your vertex, which is 2, 1. So you start with 2, 1. So you're going to create a table of graph. You're going to start with 2 because that's your maximum point. You know your graph is going to face down looking at A. So if you look at A, it still helps you to imagine where to expect your graph to go or face, okay? So you can plug in these values. 1 minus 2 is -1. Square is 1 times 3 times -3, -3, and then plus 1 is -2, right? The same thing for 3 as well. 0, plug in 0. 0 minus 2 is -2. Square that is 4, positive 4, and then times that by -3, -12, plus 1, -11. Same for that one. Okay, so let's graph it. 2, 1. 2, 1. 2, 1 right here. 1, 2, 3. 1, 2, 3. That's the vertex. 3, -2. 1, -2. And then it goes down to -11, right? Sorry, my parabola is ugly. But that should be your graph, okay? Part B, h of x is equal to x plus 1, parentheses square, minus 4. Your A is 1. So it doesn't stretch or compress. Your graph should still look the same. And shape-wise, you're just moving your graph, okay? H is -1 because that's plus 1. It's actually -1. K is -4, so your vertex should be -1, -4. So find the table of values. You just need some more points. But you're going to start with -1, -4, and then find the other values, 0 and 1. Let's go upwards because 0 and 1 are the easier numbers. So 0, if you plug in 0, that's 1 squared. 1 minus 4 is -3. If you plug in, so that's the same for that. If you plug in 1, 1 plus 1, 2, 2 squared, 4, minus 4, 0, and so on. So start with -1. -4, so I'm going to erase that. So that was for A, okay? And this is for 4B. -1, -4. So that's your vertex, and you know your graph is going to face upwards like your parent graph. You're just moving your parent graph. And then you have negative. So 0, -3, 1, 0, 1, 0, and same here, same there. And then you can move. You can keep going with 2 if your graph is still remaining. 2 plus 1, 3, square 9, minus 4, 5. And that's the same as negative 4, right? 2, 3, 4, 5. And there we go. And then you try to draw the nicest little parabola. There we go. Okay? So that should be the graph of chord B. So first step, identify all the important numbers, especially vertex. And then you're going to make table of points, and then you're going to graph. Okay? Remember this. Alright, example 5. Use vertex form to solve problems. Deshaun and Chris are playing soccer. Chris takes a shot on goal. Deshaun is 3 feet in front of the goal and can reach the top of the 8 feet goal when standing directly beneath it. Can he block the shot from his current position without moving or jumping? That's an application problem. So we see that the ball is making a parabola, right? The half parabola here. It has a point of 2, 1.2, and the vertex, the maximum point, is 16, 11. And you know the parabola is going to face downwards, so your A should be negative. So you can describe the parabolic path of the soccer ball using quadratic function. Very common application. The vertex of parabola is given, right? So you can just plug that into the vertex function, the vertex form, where h is 16 and k is 11. So you have a parentheses x minus 16 squared plus 11. You can just substitute h and k. And then pick a point. There is another point given, and you can figure out what A is, because that's not a complete equation. That is still a form. It's not complete. You can't just get rid of A, because if you do, you're still saying, oh, A is 1. But you don't know what A is equal to. So you have to figure that out in order to complete the function. Otherwise, it's not a function. You can only have 2 variables. Right? F of x and x. So choose a point when x is 2 and y is 1.2. You will have an A that makes that true, right? So substitute that in and solve for A. A is negative 0.05, and that should work for all the other points. So just choose any point on the equation. If it is a perfect parabola, it should work. So using that, you fill in the last information in, and that is your parabola. That's your function, quadratic equation. Okay? And now you can use this function to find the altitude of the ball at Deshaun's position. Deshaun is about 22.53 feet, right? Away from Chris, and he is 3 feet in front of the goal, which is at exactly 25. So yeah, so 3 feet in front of the goal means 25 minus 3. That means 22, and can reach the top of 8 feet goal when standing directly beneath it. So that should be 8 feet. Okay, can he block it? So we want to see where the ball is going to lie here. Okay, plug in 22 into x, and then figure out your y, your function value for the function, which is 9.2, which means the ball is going to be around 9.2 above the ground, but he can only reach 8 feet above the ground, right? So the ball is actually going to be above his reach. So when the ball reaches Deshaun, it'll be about 9.2 above the ground, which is above his 8 feet reach. So he probably wouldn't be able to block Chris's shot from his current position without jumping or moving. So now, are we ever going to have enough time to do this while playing soccer? No, but this is still a great application for us to think about it as a project, right? And analyze their positions, how they play, and a lot of that. So it starts with this kind of example. It doesn't always have to be practical right away, but when you start with these kind of examples and then move your way up, you can build a rocket eventually. That's the goal. Let's look at try number 5. Okay, if Dishan does not block Chris's shot, will it be a goal? Explain. So now we know he probably won't be able to block it. Would it be a goal? Would it always be a goal? It could, but depending on the goalpost, right? Right now, at Dishan's position, it's about 9.2, right? Would it hit the goalpost or would it go in, right? That's the thought process we want to think about. So it could, if he doesn't block it, there's a good chance that it's gonna make a goal if it doesn't hit the goalpost, right? So the ball will go in the goal because at x equals 25, we want to figure out the height, and we want to see if it is about the height of the goalpost. So use the equation again and substitute x as 25, because now we know goalpost is going to be exactly around 25 feet from Chris, right? So if you substitute that into the equation, f of 25 would be about 6.95 feet. Okay, so that means it's gonna make the goal. It's probably gonna make the goal. There's a pretty good chance it's gonna make the goal. Okay, so that's how we can see, we can calculate and see if it's gonna make it or not. Let's put it together and write it down. So you can say, yes, the ball will go in the goal because at x equals 25, which is where the goal post is, the ball will be 6.95 feet above the ground and the goal is 8 feet high. There we go. So that was example 5 and try number 5. And let's summarize our lesson. We learned the vertex form of a quadratic function. There were lots of information, a, h, and k, but if you remember what they represent and what they do to the graph, you'll be able to use it very well. So always remember your parent function is x squared for a quadratic function without any transformation. A changes it, h changes it, k can change it, right? So A will change the shape of the parabola. H and K will shift your graph left or right, up or down, so horizontally or vertically, okay? So H stands for horizontal transformation. K will be vertical translation. And A will be your shape of the graph. And compared to the parent function, you can use those information to compare them. Okay, and also if your A is negative, then it's a reflection, not a stretch or compression. Okay, so for A, there are two things you need to look at: the absolute value of A, the magnitude of A, or if A is a positive or a negative. Okay, in this case, if it's a negative, it's a reflection. Okay, That was lesson 8-2, quadratic functions in vertex form. Great job, guys. If you have any more questions, please ask Ms. King in class, and I'll be happy to help you. Otherwise, we'll move on with the next lesson in the next video.